Good morning. So we are roughly in unit 4 now discussing solar concept of how to get that into cars. So in that discussion, we are almost near completion. So let's uh, see where we are now. So what we've done is we've looked at vehicles, we've looked at power train, how to get calculate the motor. Then we've looked at how to look at the energy trains. This is how we went. Then in the last couple of sections, we started looking at some experimental techniques which are most likely in the future. The first part we looked at fuel cell. The second, which you are discussing now, is the solar car. The concept of a solar car. Basically, they are electric powertrains, but inside that, can we have renewable power on board? So this was the concept of a solar car. So you're looking at the state of art today, what sort of calculation needs to go in, what is the technology that we know. So that is what is being discussed. We still have to plan our CIA 3. So on that front, we will have CIA 3 on 29th November 2021. So this, I think, is a Monday. So we'll have it during our class. So what we will do is we'll plan this test. We'll continue with our combination of CIA paper. The portion will be after CIA 2 till unit 4. Okay. So when I say after CIA 2, so you have taken a test up to generator topic alone in unit number 3. So the batteries, ultra capacitors, fuel cells, and solar cars. So these would be the portion for CIA 3. Okay, so it is after CIA 2. We are talking about CIA 3, 29th November 2021. We'll post this in the GCR also for the ones who have missed here. Now, let us, so I understand there were some challenges in CIA 2. We will release the marks by the end of this week. And those with specific queries, so we'll address that on a case-to-case basis. We will take that up. And just so we clarify, your CIA marks is average of 3 CIAs, what you have written here. Is going to be an average. Okay, so that there is no change in that. After this, we will propose one assignment. We will help you with that process. That assignment will carry the 5 marks. So we expect this assignment to be submitted before the last date. Okay, so that will carry 5 marks. CIA marks will be 20. This is an average of 3 CIAs made to 20. Assignment will be a marked assignment, 1 marked assignment. We'll share that once we finish uncovering the portion. That would be for 5 marks. So this is how we will calculate your internal component of 25. Your end semester will be of 75. As we have said before, we are going as per the plan which we have discussed. And since we got an update, our last online class will be December 4. Once we complete unit 4 uncovering, we will do a short revision of sorts, and we'll help you gather everything around and put it together in the form of an assignment. So this would be a self learning kind of assignment which we expect you to do. It will not be time consuming, but it will definitely require you to think. Okay, so that sort of assignment for 5 marks. So I will stop here. If there's any other question that comes up, you can post it in the GCR. We'll discuss about it. And if there's anything now that you want to ask, you can ask me, whoever is here. CIA 3 marks calculation, ENSUM split up. I think I've given you the ENSUM paper pattern also, so how it is supposed to be. So I suppose there is no doubt. If something comes up after discussing with your classmates, please feel free to write in the WhatsApp group, or you can put it up in the GCR. One of us will look at it. We'll definitely respond to it. Okay. I will stop here. Mehboob, you can take over now.
Yeah, thank you. Yeah, good morning, guys. So today we will be discussing uh, the concept of uh, MPPT. So if you just go back to the last class and the basics which we have discussed in the earlier class, the concept of the photovoltaic cell. Uh, just like uh, so we'll be getting the solar irradiance, and then so just we'll be having some panel of which is having like cell 1, cell 2, cell 3, 4, 5, 6, 7, 8, and 9. So these are the like an a series and a parallel combination of array, right? So in generally, in the last class itself, we have discussed that even though we are the power output which you are getting is a combined one, so it does not mean that all the cells, so like cell 1, cell 2, cell 3, so up to cell 9 may not be giving the like exact output which they can. So one cell sometimes, as we have discussed, like the environmental factors like same the solar radiance, and then temperature, and then shading, and the humidity. So these factors may affect your functioning of the photovoltaic cell individually, right? So in that context, so we have discussed one example, how to like, even though if one cell, so let us take cell 2, we, for example, cell 1, cell 2, cell 3. So these cells are connected to each other. If cell 2 is shaded, or if it is not receiving the proper solar irradiance, and we know that only the C1 and C3, the combination of these two cells, will be getting as a power output. So there will be decrease in the overall power output, right? Since if there is a decrease in the power output of a solar panel, so what happens is the required, or we are not able to utilize the maximum power that a panel can deliver. So for example, we have the IV curve. So in this, the curve, so the behavior is in such way. So we know that this is the maximum power point in the IV characteristic curve, right? So all the time we need to uh, get this maximum power point in order to generate the maximum power output from a solar uh, panel, right? So this power tracking itself, uh, like we have this combination of 9 cells. If any one of the cells is not able to function, or it is shaded, or because of some technical things, if it is not able to generate the voltage and current, so we'll be not getting the maximum power point, right? So the maximum power point will be varying, right? So we'll take that as an example, and then so we'll see how to uh, track this maximum power point region and how to maintain it as a constant. So this is your IV characteristics. Okay. Now, so this is the curve we know in general. And this is here the uh, short circuit current ISC, and this is the open circuit voltage, right? And the maximum power point will be of somewhere here, right? So this will be a maximum power point of this curve. Now, if I draw the like a load line to this, which is passing through this point, and this is called as a load line, right? And this load line actually it will be varies depending upon the current and voltage, right? So if I just take an example, if this is your photovoltaic panel, okay, or solar panel, and these are the output terminals. So here just we are connecting to a variable resistor. So this is R naught. Now the current direction is in this way. And we'll be measuring the voltage across these two terminals, that is V. So if I start continuously varying the R naught, okay, see, then the if you take the slope here, so here it will be delta I, and the horizontal will be delta V. See the ratio delta I divided by delta V is your impedance R naught, right? Now, if you just plot the parallel PV curve in order to get the maximum power from the curve. So, we know that the curve will behave in such a way, right? And as we see that the maximum point, so it means that somewhere tangent to this curve. So this will be the our maximum power from the panel, which we can get from this, right? So same thing, the maximum power point and the maximum power output from the panel are in line with each other, right? Now same thing, if you just plot it in other directions onto the vertical axis, that is current, so you will be getting the maximum current. And if you just plot onto the x-axis, you will be getting the V max. So that's how you will be getting the your maximum power point, and therefore you'll be getting the power output there, right? Now we'll see how, if this load line, if this is like goes very near to the short circuit current, and if it is goes very near to the open circuit voltage. So case number one, we'll consider as a case one. I and V. Uh, so this is your maximum power point. This is the actual curve we want. This is the actual load line. Now, at this point itself, we are getting the maximum power output, right? Now, if this load line, it means that your delta I, delta V, if this is very close to, or if it is goes in this direction, it means that I'm actually, if it is moving in very near to the short circuit current, just I'm varying the resistance. Okay, since this is a variable resistance, the curve will be, it shifts here. So actually your this ratio will be decreasing. So if it is very close to I, that is, if it is false here, okay, it means that on I, your delta V will be 0, right? So if delta V is 0, what happens is your R naught will becomes 0 here. If same thing, if shift somewhere here, here your actually your delta V I will be 0. Now, when your actual load line, it shift it somewhere between the short circuit current and the maximum power point, and these are our maximum current which we can get, and maximum voltage. So here I max and then V max. See, if you just correlate parallel to your power plot, the power which we are getting here, this is the maximum power which we are getting from the curve. This is P max. So, but if you just compare with the earlier, at the top, this is, if I consider P1 and this is P2, see, there is this much of power loss happens, right? If this is goes very near to the short circuit current. So, if our maximum power point, if it is travels any one of the path above your MPP, so there is like the power which we are not actually getting the maximum power output from the panel. Now, if you take another case, that is case 2, case 2. So I and V. And 0. So this is the maximum power point. and this is your load curve, like power curve. So this is the maximum which we want. Now, if the curve is very close to the in this direction, that is the direction of open circuit voltage, this will be your maximum power point. So this is your actual load line, and this is your like transferred the newly which we are getting the power operated power because of changing any one of the environmental factors or damage of any one of the cells in the array. So this will be your maximum current, and this will be your maximum voltage, and the power which we are getting is also lower. See, a lower power region we are operating the, or the lower power which we are getting from the solar panel. So like it is, if you, if it is goes like on the v, the horizontal axis, here our delta I will be 0, your r naught will be infinite. So right, so you'll be getting infinite resistance, the variable resistance. Now, even in the case 1, we are not able to getting the maximum power point. Even in case 2, even though we are getting maximum power point, but we are not getting the maximum power output, right? So the maximum power output is varying along with the maximum power point. Okay, the output power, P output, is depends on the maximum power point, so which we can call it as the operating point. So there is, since it is a varying, now all the time we want the operating point should be the maximum power point. So I want to operate my the or the solar panel to be at P max only here. It means that always I want to maintain the load line to be constant. Okay.
Subhani, are you there?
Yeah. So just there is like Wi-Fi off.
Oh, okay, fine, fine.
Just 2 minutes, guys. Yeah. Yes. Yeah. Now, in these two scenarios, in case one and case two, both the cases, even though we are getting the maximum power point, but we are not getting the operating the panel in the maximum power output region. Now, in order to have this maximum power all the time, we need to maintain the maximum power point to be constant. So it should not be vary along the curve. So if it is varying along the curve, so we will be not getting the maximum power from the panel. So that's the thing which we can get from this curve. Now, what we can incorporate in order to maintain the solar panel to produce the maximum power output, right? So that's how we have introduced this concept of maximum power point tracking. So we need to, like, it's a kind of tracing. Then we want to, even though there is a varying in the load, so we have to, uh, by some other devices, we will be maintaining the maximum power point to be constant to be getting the maximum power output from the solar panel. It means that we need to incorporate another device. Let us take the solar panel. So this is your solar panel and the terminals. Okay. So in between your resistive load and your solar panel, we are incorporating another device. Okay. Now we will be getting the output from here. So still it will be the variable resistance. And this is our power interface. This is our power interface. And this also we have to give some sort of control input. Control input. And this is your current direction, and we'll be taking the voltage across these two terminals, and this is called as a terminal resistance. Okay. Yeah. Now, how this power interface, by using this power interface, we need to get the maximum or things all the time the load. So we can call it as a load, a resistive. So load in the sense, in generally, we will be measuring or will be dealing with the drawing of current. So how much amount of current is drawn of current. So that's the term load defines. So it means that even though the load changes, right, all the time we need to make sure that this RT or the current and voltage which we are getting from here to be maintained constants. So here it is a variable, and here we need to maintain the constant. So even though if there is a change in R naught, so we make sure that RT should be a constant. Okay. Now this sort of a control inputs. Okay. So how we'll be dealing is actually this will be also getting the control input. That is control input. And this control input, it actually senses the output, means whatever the requirement to the load, it will be sensing that, and that will be shared to or sent to controller. Okay, and that will be giving as an input again. And this controller itself have different mechanisms of giving. So different mechanisms, right? So it can be of different types of input or controllers we can use here. So there are majorly two types. One major classification is non-isolated. So in this we have boost type converter, which is step up, we'll call it as. And the second one is the buck type, that is step down. So mostly you might have heard in the concept of transformer, right? And then third one is the buck boost. Buck boost. And the second classification is isolated type. In isolated, we have the converters of flyback, flyback, and then forward converter, and then push pull. And then we have half bridge, and then we have the full bridge. So all these are the converters. So these types, either the non-isolated or isolated, so this will be chosen based on the application demand. So based on the application demands. It means that directly we can call it as the what type of the load we are operating, right? So mostly, if since we are using the electric vehicles, so the motors of a DC motor, we will be using a power interface of DC to DC converter here. So DC to DC interface we'll be using. Now, what if we have a load of or the application demands an AC input. Okay, then we have to use a DC to AC converter, or else we have to incorporate an inverter. Okay, so based on the application and the type of load you're using, you can use different types of the power interface, right? Now we'll see how this power interface will be actually maintaining this RT as constant by changing the variables or taking input as a variables. uh, we have a solar panel, and the power interface, and we have a varying load here, and this is your solar panel current direction RT. So we'll be measuring the voltage V, right? Now, in order to maintain this RT as constant, what we'll be doing is we will be uh, taking a current I as an input. This is one input, and V as an another input. So V as an another input. So I and V we are taking as input, and we will be processing these two input. So this is a kind of a processor, which will be process the variables appropriately. Okay. Now these two process like appropriate data will be uh, taking as a reference, or we can call it also like a reference generator. Now, whatever the values which we have taken the current and voltage, and after processing that, we will considering as a reference. So that will be the uh, reference value. Now, this reference value will be sending to as an input to the and another variable. It is called as a feedback variable. Okay. Now this feedback variable will be also having some sort of input. Okay, so this input could be from your load which you are using, right? The demand. So we are getting the demand from here, and there is a reference here, right? So there is a demand and the reference, or this demand we can call it as also an actual load which we want. So definitely there will be of difference here. So the reference and the demand or the actual load will be the difference with which we will be calling it as an error. Okay. And now that error we are giving to the sending to an PI controller. Okay, so I hope these are controller which will be calculating that error value, and that error the corrected value will be sent to the input as your power interface power interface. So these adjustments will be done by your power interface. So by means of that processing, it will make sure that all the time your RT to be maintained constantly. So RT maintained things constantly all the time. So then we can able to get the maximum power from the VI curve, right? So this is how we will be. So actually, this controller we have like several algorithms. Okay, so the algorithm can be you can build up. So let us take an example, a rough example. So as we have discussed earlier, we have 9 cells. So C1, C2, C3, C4, C5, C6, 7, 8, and 9. So let us take that a C1 will be producing a voltage of V1. C2 will be producing a voltage of V2, C3 of V3. Likewise, we'll be getting uh, till C9 voltage V9. So any one case, like if I take some cases V1 will be greater than V3, or sometimes V2 will be same, V1 will also be greater than V2. So if there is a variation, or in case we can even in the same series, we can take it as a V2 can be greater than V1. So V3 or V2 can also be greater than V3. Or in some other cases, like otherwise. So V3 can be so less than and less than. So V3 greater than be V2, and V3 can also be greater than V1. So likewise, in each string, we have there are like several combinations can be possible. Combinations can be possible. Now, even if cell 2 is not able to function properly, so we can omit whichever is coming under V2. So likewise, we'll be doing uh, for string 2 and string 3. And now this several arrays, we will be forming a panel, right? And this sort of inputs, we need to generate a code for this kind of varying in voltage. And that will be giving as an algorithm where your controller will works and will be giving your input to your power interface, right? So this is how your maximum power point tracking so is functions. Okay. And now the next, if the point of reliability. Reliability. So what is meant by reliability, right? So the rough meaning is if any device if it performs consistently, okay, how long or the if this device MPPT will be performs consistently. What happens if this MPPT fails? Okay, so until it performs the consistently, it means that if it is able to track the maximum power point consistently, then it is fine. Then what happens if your MPPT fails, right? So first requirement is this: the reliability must be high. Okay, must be high. And 1 minute. Yeah. So one point is it must be high. So if this MPPT fails, what we need to do is what happens in the next sequence is its string also will be failed. Its string also fails. So why? Because most of the time we will be connecting this from string to bus. Okay, major bus. So bus in the self, if we have a solar panel, so if this is a series of cells, all the series of cells are connected to a main bus. Okay, so we'll call main bus a string or array. So that's how it will be formed. And now this, if this string fails, since this is connected to cells, so cells will be producing the current I, right? And it will be cuts the power by a large fraction. Okay, so if this power cut happens, so there will be drop in maximum power output of the panel, right? So there is a linkage internally in the panel, so we'll be losing the power for certain period of time, that is t. So whenever if you notice the uh, MPPT fails, you need to either change the MPPT. So we have to replace a new MPPT, then uh, it can be tracing the maximum power point, right? In market, so this is like an overview of your MPPT. So somewhere you can also find along with MPPT and another devices PWM, so which is uh, pulse width modulation. Okay, so that is in short form we'll be writing as PWM. So actually here it extract the maximum power from the solar panel, but this PWM, what it do is it only utilizes the power generation from the solar panel and it will charge the battery, that's it. Okay, so it will not trace the maximum power point to generate the maximum power output. That's the difference. And this efficiency is uh, of 70 percentage alone. And your MPPT, almost it will be like 90 to 95 percentage of efficiency we can get from an MPPT. It means that if your panel is generating 100 watts, so this will be charge the battery to only 70 watts. So the 30 watts is like waste is going here in terms of in the PWM. Here, if a panel is generating 100 watts, we can able to get 90 to 95 watts. Okay, so probably 5 to 10 percentage of loss we can get here, right? So, but in general, this MPPT will be like costlier and it also added weightage to the vehicles, right? If it is like if you are installing the power for an home, so can be a better option. But if you are uh, looking for any application point of view for the vehicles, it can be an added weight. So depends upon the how many panels are required for the to run your vehicle, right? So this is what for the topic under the uh, maximum power point tracking, right? Uh, yeah, so that's it for the today's class. In the next class, probably we'll be discussing the uh, cell efficiency and then the cost comparison. Okay, so if possible, if I we can also do it for the panel. Okay, then we can wind up the solar cells or solar cars topic. Uh, so so that's what for the today's discussion. So if you have any doubts, you can ask. So if not, can leave. Thank you.
Thank you, sir.
Yeah, thank you.